Hi there, this video is going to walk through an introduction to chemical formulas. So as we all are aware, atoms come together to form molecules, and it's the chemical formula that tells us how they're coming together to form our molecules. Let's look at carbon dioxide for an example. So CO2 would be the chemical formula for carbon dioxide. We'll talk later about how those atoms are actually put together in space when we talk about our molecular geometry. But for now, let's just focus on the chemical formula. So what this tells us is that we have one carbon atom that combines with two oxygen atoms. Okay, so here we've got one carbon atom and two oxygen atoms is what that chemical formula tells us. Now this is what we would call one molecule of CO2. Okay, so we can have a bunch of CO2 molecules floating around in the atmosphere, and in fact we do have a lot of CO2 molecules floating around in the air. Okay, but each one of those molecules is comprised of one carbon atom and two oxygen atoms. So anytime you want to know what your molecule is made up of in terms of atoms, you just want to look at the chemical formula. So one that you might be familiar with from maybe a biology class is glucose. Okay, so if you look up the chemical formula for glucose, or if you remember it from biology, you know it's C6H12O6. Okay, so we know that glucose contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Okay, now what this does tell us is the chemical makeup of our molecule. What it does not tell us yet is how all of those atoms are arranged in space. So we'll get to that later, okay, but for now, we'll just focus on identifying the numbers and types of atoms that we have in our molecule. Okay, so these subscripts that you see in your chemical formulas tell you the number of atoms that you have in your molecule. Okay, so now that we know our formulas for our different molecules or compounds, we can start to use that information to determine the mass of these different compounds. There are a couple of types of masses that you're going to see referenced depending on the resource that you're using or the type of compound that you're looking at. Okay, one is called the formula mass. Okay, this is the mass for one unit of a substance's formula. Okay, so you're just going to add up all of the average atomic masses for each atom in the formula that you have. Okay, this will be valid for any substance, whether it's a molecular or an ionic substance. Okay, the other one is molecular mass. This one's a little bit more specific. It only pertains to molecules. Okay, so you just have to be a little bit careful here with your language. So molecular mass is the mass for one molecule of a substance. So again, you're just going to add up all of the average atomic masses for each atom in your formula, but just be careful that you're only using this to describe discrete molecules. Okay, it's not going to be valid for ionic compounds, so things like sodium chloride. Okay, that actually form what we call unit cells. They form large 3D structures based on their individual formulas. Okay, so just be a little bit careful on that. So formula mass is valid for anything. Molecular mass, be careful, that's only for covalent molecules, so not for our ionic salts. Okay, so for an example, we could say NaCl would count as a formula mass, okay, but it would not be valid as a molecular mass, right? But CO2, right, could be either one, okay? So just a reminder those ionic compounds are not going to fall under our molecular mass category. A lot of people will use them interchangeably, okay? I will probably slip back and forth between the two without thinking too much, but just so you're aware of the distinction between a molecular mass and a formula mass. All right, let's do some practice here. So now that we are familiar with what the chemical formula represents, right? It tells us the number and types of atoms in our compound. Now we can use that information to calculate molecular masses or formula masses, okay? So we do that using the tool of our periodic table. All right, so now is the point where you want to get your periodic table and start locating on your periodic table where your atomic masses are. Okay, so we're going to be looking for atomic masses for hydrogen, nitrogen, and oxygen. Okay, and then we're going to add them all up, make sure you account for the total number of atoms of each one you have, and then that will allow you to calculate your total molecular mass for that molecule. Okay, so let's start with nitric acid. All right, so we have one hydrogen, so we've got 1 times, if you look up the molar mass of hydrogen on a periodic table, you'll see it is 1.008, and that is in units of, again, atomic mass units. Okay, very small. We're talking about 1 hydrogen atom, super tiny, on the order of 10 to the minus 27 kilograms. Okay, so we've got 1 hydrogen atom, and we're going to add in 1 nitrogen atom. Okay, so if you look up nitrogen on your periodic table, you'll see you have 14.007 AMUs. Okay, and then we have 3 oxygens. So we want 3 times the mass that is listed for oxygen, 15.999 AMU, according to my periodic table that I'm looking at. Okay, so one thing to keep in mind is that depending on the specific periodic table that you're using, you might have a slightly different value that you're putting in here, okay? And sometimes if we're just doing a quick calculation, maybe we'll just round up to the nearest whole number. Okay, so 1 or 14 or 16, okay, it just really depends on the application for what you're doing. But for our first examples here, we'll use the full values that we have on the periodic table. Okay, so if you punch those numbers into your calculator, you should end up with, oops, 63.012. And don't forget your units. We want to know what we're dealing with. We are currently in units of AMUs, atomic mass units. All right, so why don't you pause the video and take a few minutes to see if you can work through the calculations for the molecular masses of caffeine and molecular nitrogen. So one thing that I'll draw your attention to here, we're talking about molecular nitrogen. So certain elements are naturally found as diatomics, okay? So there's a few gases that you're always going to make into a diatomic molecule when it's in its molecular form. So it's the nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, they make a little 7 in the corner of the periodic table. We'll encounter this more as we go along, but just be careful. So here we are looking at N2, okay, diatomic nitrogen. All right, so take a minute, do your calculations for these, and we'll check back in a second and see how you did. Okay, how'd you do? So here are my answers for the last 2 examples. Okay, so caffeine, much more complicated chemical formula, okay, but you're still using the same method. So just take the number of atoms you have, okay, so 8 carbon atoms, multiply it by the atomic mass for carbon, and then so on for each part of your chemical formula. Okay, so hopefully you ended up with 194.194 AMUs for caffeine. Okay, and then again, nitrogen, simple calculation, okay, but just reminding yourselves that molecular nitrogen has 2 atoms, so don't forget to account for both of them in your calculation there. Okay, hopefully that helps you to feel comfortable in calculating molecular masses. Okay, this is going to be a really powerful skill to have under your belt as we move forward in our chemistry journey, and you'll see that it's going to pop up a lot as we go along. So make sure you feel comfortable with this and keep doing some practice with these on your own.